Hello, welcome to the Virtual Beach video tutorial series. These tutorials were created with the support of both the University of Wisconsin Sea Grant Institute and the Great Lakes Observing System. My name is Sonia, and I will be leading these tutorials. At the website virtualbeach.org, you will find all of the video tutorials, many helpful hints, and links to data sources. These tutorials are intended to walk you through the Virtual Beach software that was created by the US EPA. Virtual Beach is a predictive modeling program that can assist managers in making advisory decisions at fresh and saltwater beaches. With this software, beach managers can create models to predict bacteria levels at a beach. This tutorial, Building and Evaluating an Anytime MLR Model, walks you through the fifth of 6 modules demonstrating how to use the Virtual Beach software. If you have not completed the 4th tutorial, Data Preparation MLR, complete that module first. You need to use the project file created in that module for this current tutorial. Detailed directions for this module are available at virtualbeach.org in the training section. Under the subheading Virtual Beach Step-by-Step Training Modules, select the Building and Evaluating Anytime MLR Models. Either open the PDF on your computer or print it so you can follow along with these instructions. By the end of this module, you should be able to set up and run an MLR model, remove extraneous and insignificant variables, evaluate the model, set MLR decision criteria, and import data to validate your model. To set up and run an MLR model, open the file saved at the end of the Virtual Beach Data Prep MLR module. In the Global Data Sheet tab, click the Go to Model icon. Click on the MLR tab. A copy of the main data table labeled Data Manipulation will open. Click the Model tab. Under Available Variables, Control-click Variables for building the model. Select the summary variables, Cloud Cove, Clarity, Alge Nearshore, Alge Beach. Click the right arrow button to move the selected variables to the right-hand panel. Do not select any variables from the Available Variable box if those variables were used for a longshore and offshore vector calculation or for other manipulations. Do not include the variables wave height, feet, gulls, opaque, turbid, wave height, wave direction, wind speed, wind direction, current direction, current speed, trib min 24 and trib max 24. Highlight any of these variables if they have been moved to the independent variable box. Then click the left arrow button to return them to the available variable box. In this example, there will be 100 independent variables. Virtual Beach calculates how many MLR models can be generated with 100 variables and displays that number below the variable selection box. In this example, 20 septillion models can be created. Under Model Settings, click the Control Options subtab to view options for the model building and optimization routine. Note that the recommended maximum number of variables for an MLR model with 281 observations is only 29, not 100. Click the menu under Evaluation Criteria to view the options for evaluating and ranking models. Keep the default choice AIC. Click the Genetic Algorithm subtab. Check the Select Seed Value box. Enter the number 1 in the box. Virtual Beach uses a random number generator to produce numbers for creating models. By setting the seed value to the same number, the analysis can be reproduced by others. Click Run. Virtual Beach will now begin analyzing various combinations of variables and calculating the corresponding equations. While the optimization is running, you will see a blue line progressing across the graph. The y-axis, fitness, shows the successive model's values with respect to the evaluation criteria, in this example, AIC. When the model building routine is completed, a top 10 list of the models with the best fit will appear, ranked by AIC value. Click the Variable Selection subtab to return to the list of potential variables. You will use the IV filter tool to remove less significant variables from the list. Near the center of the screen, click the Clear List button. The 100 previously selected independent variables will be cleared. With the first best fit model selected, highlighted in blue, click the Add to List button. All of the variables included in that model will be re-added to the list of selected variables. In this example, 11 variables are added. Add back in the variables for each of the remaining best fit models by clicking on the next model, then clicking on the Add to List button. At the end of this process, a filtered set of 39 potential variables remains. Note that the number of MLR models possible is now approximately 543 billion. Still too many for an exhaustive evaluation of all possible models. Return to the Control Options subtab. Select the Bayesian Information Criteria, BIC, under the Evaluation Criterion drop-down menu. On the bottom of the Control Options subtab, click the Run button. When the genetic algorithm optimization completes, repeat the IV filter process to reduce the number of potential MLR models. Click the Clear List button. Highlight the first best fit model. Click the Add to List button. Again, all of the variables included in that model will be re-added to the list of selected variables. Add back in the variables for each of the remaining best fit models by clicking on the next model and clicking on the Add to List button. After completing the second independent variable filter process using the more restrictive BIC criteria, there are now 16 potential variables, or 65,535 potential MLR models. That is a small enough number for an exhaustive evaluation, so now we can focus on improving the model's predictive power. Return to the Control Options subtab. This time, select Press under the Evaluation Criterion drop-down menu. Click the Manual subtab. Check the Run All Combinations box so an exhaustive evaluation of all possible models will be conducted. Click the Genetic Algorithm subtab, then click Run to create the new model. Click the Cross-Validation button. In the Cross-Validation pop-up window, set the number of observations used for testing to 70, approximately 1/4 of the total 281 observations. Set the number of trials to 500. Click Run. The top best fit models will each be rerun 500 times. In each run, 70 of the 281 observations are randomly removed and used as a validation dataset to which the model's results are compared. Once completed, click on the MSEP column. This will sort the models by the mean square of their predicted errors. Identify the model with the lowest MSEP by looking at its corresponding fitness number and click OK. On the best fit list, click the model corresponding to the lowest mean square of predicted errors found during cross-validation in the previous step. Sometimes the model with the lowest MSEP is the same as the original best fit model. However, the two will not always correspond, as in this example. The next step is to set the best possible decision criterion for this model. Under the Fitted versus Observed subtab, click the drop-down menu under Select View. Select Error Table CFU as DC. Here is where you search the list of decision thresholds to find the optimal balance of at least 0.5 sensitivity and 0.9 specificity. An easy way to narrow down what range to look for is to look at the smallest number in the fourth column, titled Total. This total is a sum of false non-exceedances and false exceedances. The decision criteria with the lowest total here is 2.2216, with 18 false non-exceedances and 8 false exceedances. What is confusing is that the decision threshold is listed as the log value, not the untransformed value of the decision criterion. For clarity, the decision threshold is converted in this chart. The decision criterion that will give the best model is somewhere between 125 and 221. Return to the Plot Predicted versus Observed graph by selecting that choice under the Select View pull-down menu. To the left of the plot, under Plot Thresholds, the default of 235 does not give the optimal sensitivity and specificity. Change the value to 125. This value is 10 raised to the power of 2.0978, the log 10 value given in the error table CFU as DC. Highlight the radio button in front of None under Threshold Transform and click the Update button. The value of 125 CFUs gives 13 false positives, 0.946 specificity, and 16 false negatives, 0.55 sensitivity. Change the decision criterion again to 130 and a slightly better result is seen. 12 false positives, 0.9 specificity, and still 16 false negatives for 0.55 sensitivity. Change the decision criterion one last time to 135 and a slightly better result is seen. 11 false positives, 0.95 specificity, but still 16 false negatives for 0.55 sensitivity. You can continue to experiment with other decision criteria to see how sensitivity and specificity change. For this example, we will stick with 135. View an MLR model within the Prediction tab. Click on the Prediction tab at the top of the page. Under Available Models, click MLR in the box. An equation will then appear in the box to the right of the model. The text box at the top center of the Prediction tab contains the mathematical expression of the selected model. The bottom half of the Prediction tab is the predictive record. Change the decision criterion from the default value of 235 to the value identified earlier, 135. If you do not remember the value identified, return to the MLR tab to view the plot showing the threshold value. Now import historical data to validate your model. On the Prediction tab, click the Import Combined icon. Navigate to the Excel file VB Training Data MLR. Click Open. Select the worksheet MLR Validation Data 2016 and click OK. If this is the first time these data have been imported into the Prediction tab, the Column Mapper window will open. Imported variables must have the same names of their corresponding variables in the model. You must map or match these variables. Click OK. The explanatory variables, or independent variables, are now in the left-hand panel. The E. coli values are in the next panel. Click the Make Predictions icon at the top. The predictions are now in log scale in the right panel. Right-click on the top of the Model Prediction column and choose None to the right of Display Transform to make the E. coli prediction appear in a non-log scale. Click and drag on the solid blue section separators to enlarge the width of the prediction panel and reduce the width of the independent variable panel. Adjust the width of the columns in the various panels so you can more easily examine the daily results. Ideally, you will view both the observed E. coli in the middle panel and both exceedance probability and error type in the right panel. To evaluate performance visually and numerically, click the plot icon. A plot of observed E. coli values on the x-axis versus predicted E. coli values on the y-axis appears. The decision criteria, the horizontal blue line in this example, 135, and the regulatory standard vertical green line is 235. In 2016, 28 observations were made. None of the observed bacteria samples were over 235, so no false negatives or missed exceedances were possible. The sensitivity is then indicated as NaN, not a number, since the denominator of sensitivity, all observed exceedances, is 0 in this example. There were 3 false positives, resulting in a specificity of 89%. When you have completed your evaluation, click Close to return to the predictive record. Here are 2 examples of incorrectly predicted exceedances. One at 53.94 and another at 67.62. To export the predictive record for future reference, click the Export as CSV icon. Name the file something like Validation 2016 MLR Blue Harbor Beach and click Save. Remember to save your model often. Since you have now completed your model, you can move into the last module, Now cast predictions.